We are live in 3, 2. Welcome, everybody. Today we are very excited to have Antonio Carta present their paper XModel, Continual Learning from a Stream of Trained Models. Antonio is an assistant professor at the University of Pisa, working on continual learning and more. Antonio, we're very excited to have your talk today. I understand that you're going to propose and talk about a new, exciting, challenging problem in continual learning. So I guess without further ado, please take it away.
Okay, thank you for the introduction. So this is from our last recent paper on this XModel continual learning, but more in general, it's like this research line that we are starting in Pisa about distributed continual learning. So having the ability of multiple continual learning agents to share and reuse their knowledge over time. This is joint work with Andrea Cossu, Vincenzo Lo Monaco, and Davide Bacciu from the University of Pisa. So I have been already introduced, but I just want to let you know that I'm also the lead maintainer of Avalanche, which is the continual learning library from ContinualAI. And most of the stuff that I'm going to talk about today is going to be put inside Avalanche. We have already the benchmarks and the Pretrained models, so you can use them. They are ready to go. They will be downloaded from the web server, so you don't have to train them yourself. And at some point, we will also put the training algorithm, which is already public, but not inside Avalanche. So the talk is divided into 3 parts. First, I will talk about continual learning and the current view of continual learning, so the way in which most of the people working on it are currently thinking about continual learning. Then I want to introduce this XModel continual learning. So I want to show you why we believe this is important and what are the challenges that are important, but currently we are not tackling. And finally, in the conclusion, I will talk about the opportunities that this paradigm opens up and some of the challenges that we still have to solve and we don't know how to solve. So they are good research problems if you want to try them. So continual learning with the current view, first of all, you all know what a continual learning agent is. So you have some kind of model learning from data, and the data is changing over time, right? And the objective is to learn the new data without forgetting the old one. And like this is very obvious to you. And just to fix the notation, in this paper, we use the definition of continual learning as a stream of experiences. So this is the time index. At each time step, you have this box, which is the experience. And inside the experience, you have all the information that you need to learn. So for example, in the supervised continual learning, you may have a data set. In the online continual learning, you may have a single example. In the reinforcement learning, you may have a reinforcement learning environment. And we will see later that in our setting here, we will have only a pre-trained model and no data, actually. So here you have some examples in the supervised continual learning scenario, but you are all very familiar with it, so I'm not going to go into detail. So there is this view of continual learning, which is the biologically inspired view. And I think if I ask to most people following this talk or most people working on continual learning, they're going to say that like in order to do continual learning, you have to be somewhat biologically inspired because at least the best continual learning model that we know up to now is the brain. So there is this very strong idea that somehow we have to imitate some of the biological mechanism of continual learning, which kind of makes sense, but maybe it narrows down a little bit what continual learning is. So if we start with this view of continual learning as a biological agent, like an inspiration from biological agent, we end up with this agent-centric continual learning. So you can think about a continual learning algorithm as some kind of algorithm training a model which is a single agent. And here I put the example of the robot grasping objects, and in a continual learning setting, it will encounter different objects or different instances of the same object over time. And you want the agent to improve its performance by learning from this kind of stream. So in this view of agent-centric learning agent and biologically inspired, you have some desiderata that comes from the limitation of the agent and some that come from the environment. Like, for example, you may want to have replay-free continual learning because the brain doesn't store exact copies of the data, and also because maybe you may have access to a generator, but not on the exact data, right? You have limited computational resources because, of course, the agent will have limited computational power. This is true for the brain and, of course, for any kind of computing power that you have. And then you have constraints from the environment, like the fact that often you don't have task boundaries, so you don't know where the shifts are occurring. And in some environments, you have only an online stream, and you can learn. You need to learn one sample at a time, so you don't receive a large batch of data, but you just see the single examples as they occur. Right. So these are the desiderata in most continual learning papers. Sometimes these are implicit, like sometimes people don't talk about limited computational resources or replay free, even though they are guided by these limitations in their algorithm design. So now what I want to argue is that while this bio-inspired continual learning is very popular and very studied, there are a lot of constraints that instead come from the computational environment, from the kind of computational infrastructure that we have today, with the Internet of Things, with the smartphone device, so the personalized devices that we have and that we need to take into account, but that maybe today we are not really considering in continual learning. So let's try to define this distributed continual learning instead. So the idea is that a continual learning algorithm is still training a single agent as before. So there is no change here, but what is changing is that instead of having a single agent, you have a fleet of independent agents. If you think about the robot grasping objects, now you have different robots that are grasping different objects over time. Like here, they are all in the same room, but you can imagine different labs that have access to different objects, and maybe different versions of the arm of the robot, and so on. And what you would really like to do is to be able to make these agents talk to each other. So if you want biologically inspired interpretation of this, it's like talking. So we want the different agents to be able to share the knowledge. But also you have some desiderata and some strong limitation in how you share this knowledge. So first, yeah, we want to share the knowledge because if an agent already learned to grasp some objects, ideally, you would like to take the same knowledge without having to redo the entire training loop, which may be very expensive. So we want the learning algorithm to be efficient, but also distributed. So in some sense, if an object, an agent already learned a task, you want to exploit its knowledge without doing the training from scratch. But also you have to consider that in most environments, these agents will be independent. Like, for example, if you imagine different labs where these agents are trained, maybe they don't want to agree on the same training protocol because each one of them, like maybe some of them have more computational power, so they can train their model for 1,000 epochs, while a smaller lab has more limited computational power. But what they may agree is that at some point they will share the model, right? So they share the model, but they don't agree on how to train their model. So this is a big difference with respect to, for example, federated learning, where you have this a centralized control. So you have the server and you have the client. Here, it's more like a peer-to-peer interaction, where the agents can communicate with each other, but they don't necessarily have to agree on everything. And finally, the last desiderata that you have is the privacy at will. So some agents may want to share the raw data, but sometimes the task that you want to solve require the use of private data, so you don't want to share it. You may want to share the model, but you don't want to share any data at all. So we need to learn without ever seeing the data. And now we come to the proposal in our paper, which is called X-Model Continual Learning. So the main use case here is the reuse of pre-trained models. In general, you know that pre-trained models encode some form of expert knowledge about a subdomain. Again, think about the robot grasping object. Each robot knows about different objects, so it's a subdomain of the entire task that you want to learn, and you already have an expert available somewhere that is allowed to share its knowledge in the form of the pre-trained weights of the model. And today we have really thousands of pre-trained models, like in Hugging Face, for example. You can just download them. Here on the bottom, it's a screen from Hugging Face. Like for some problems, you have literally thousands of models that you can download. But a very similar use case is the one where you have local personalized models. Like you may have in your smartphone a neural network that is locally adapted to your own speech pattern, for example. And at some point, you may want to share the knowledge from all these clients, but you don't want to share the data again. And let's assume that this local personalized model is trained locally on the client, not on the server. So the question is, how can we exploit its knowledge? And we have, again, a couple of desiderata. So the use of the expert knowledge, and in particular, their use over time. So it's not just for the initialization. Like in continual learning, you have that often you initialize the continual learning model from some kind of pre-trained model. This is very popular, but it's not what we want to do, because we assume to have more than one expert, and we assume that new experts come over time. So you don't have them all at the beginning. We assume that these are independent, so we make zero assumption about either the architecture or about the training algorithm. We just know that the model has been trained up to convergence on its own subdomain, right? And then we assume privacy, so the original data is unavailable. These desiderata are specific to the papers, but again, the framework is a bit more general than that. So in order to propose something that was simple to understand and easy to use and do experiments with, we said, okay, let's take a stream of a continual learning scenario like those that we use in computer vision, but instead of providing the raw data, we provide the expert model. So here the F1S is the model trained on the first batch of data, F2S is the model trained on the second batch of data, and Fi on the ith batch of data in general. So in the classic continual learning scenario, you have that the continual learning model is updated by using the raw data, while here in the X model continual learning, the model is updated by just taking the expert. And we will see in a moment the algorithm. So the paper is on arXiv, by the way, and it has been accepted to the CL Vision workshop. So this is the formal definition of the scenario. Some of you may be familiar with this definition for the classic continual learning scenario. So like the algorithm, not the scenario. In general, in the classic sense, a continual learning algorithm takes the model at the previous time step, the new data, a buffer of limited size taken from the previous data, and then optionally a task label, and it's going to return the updated model and the updated buffer. Here, the difference is that we have the, again, the model at the previous time step, but then instead of the data, we have the expert model. And we will see in a moment, this is the buffer of data, but we will see in a moment that this buffer does not contain the original data, but something else. So we have that the continual learning model never gets access to the original data. Since we have limited computational power, we assume that we cannot maintain all the experts in memory. So you see here in the algorithm definition, we only take the current model, while the previous one, the previous experts are discarded. We are allowed to maintain this limited buffer of data, which is either generated or out of distribution samples, so not the original, but some other kind of data source. And due to these constraints, we have privacy by design. So we never share the private data, which is going to stay on the source device. Like here, of course, we are assuming that the model itself is private, but for example, you could train the model with differential privacy if you care about this. And since the experts are independent, each expert could have its own privacy constraints. For example, they are not defined by the continual learning setting, but they can be defined by the stakeholder training the experts, let's say. So we propose a baseline algorithm to solve this kind of scenario, which is called X model distillation. I mean, I call it a baseline, but it's a bit more involved than a simple baseline. The basic idea is to exploit data-free knowledge distillation. And so doing the knowledge distillation, but without having access to the original data. And also you have to consider that the knowledge distillation in this setting is done by combining two different models, the continual learning model at the previous time step and the new expert coming from the stream. So we have the data-free distillation, which I think is an elegant way to solve the problem of merging these two different models because it's very general. One thing to keep in mind that was asked a lot by different people is that here we cannot really use generative model. I mean, because typically they are not available. So you have a discriminative model, but you don't have the generator trained on the original data. What you can do, if you want, is to train a generative model with data-free technique. And there are some of them, both in continual learning scenarios and in the outside of the continual learning literature. But you don't have access to a generative model trained on the original data. So what we do instead is to use synthetic data either or auxiliary data like out of distribution dataset. And basically we do all of this to stay agnostic to the continual learning scenario. So we don't make really any assumptions about how the experts have been trained or what is going to end up in the data, in the original data, what kind of shift you have. Basically, you can apply it in every scenario that you can think of. So these private sources of data are two. One is coming from model inversion techniques. So in model inversion, what you do is that you initialize an image with random noise, and you optimize it by gradient descent to be of a particular class. So basically, you use the image, you feed it to the expert model, and then you optimize you want the logits to predict the class that you want to obtain. And you do this by optimizing the pixels. And when you do this optimization process, you typically add a couple of different natural image priors, which are some regularization terms that encourage realistic images, like saying that the batch normalization statistics should be close to those of the original data, or saying that pixels that are close together should have similar values, like you see again in the original image. And this is an example of the kind of images that you cannot obtain with these synthetic techniques. You can see they are kind of noisy. I will zoom it. They are kind of noisy, but probably the expert model is able to recognize all of this correctly because they resemble the original images. The alternative source of data that we use is out of distribution data. So you assume to have a public source of data that is similar enough to the original data so that you can do knowledge distillation. For example, when we train on MNIST, we use fashion MNIST, and when we train on CIFAR-10 and 100, we use ImageNet. Okay, so just to recap the X model distillation algorithm, basically you iterate over the expert in the stream. Then here you update the buffer. So if you are using the synthetic data generation, you have to generate the data using the new expert, and then you have to add the new data to the buffer by removing some of the samples and to make space for the new data, and then combining the previous data with the old one. And then once you have updated the buffer, you do the knowledge distillation. So you sample from the buffer, you compute the output from the student model, the continual learning model. To get the target, you have to compute the output from both the previous continual learning model and the current expert and combine them together. Then you compute the loss, which is a knowledge distillation loss. We actually use the mean-square error, but I mean, it's a technical detail that is not that important. And then you do the gradient descent, and you repeat this for how many iterations as you want. So we did a couple of experiments on different scenarios, and we provided also some simple ensembling baselines just to have some form of baseline that we can use to compare. Because so the problem is that most of the continual learning algorithm that we have in the literature are not applicable to this scenario because, of course, they need the real data, so we cannot apply them here on a stream of models. So we have some ensembling baselines which take unbounded memory, so they keep the entire stream of experts and they compute the output with this ensemble. Like the oracle is basically the upper bound, so the one where you always choose the correct expert. It's like having task labels in some sense. Then we have the average, where we just average the output, and the mean entropy, where we take the output with minimal entropy. So this is just to basically like saying, take the model which is most confident. Then we have the ensembling with fixed memory, so where we average the parameters. And this is very similar to what is done in federated learning. So in federated learning, often you have some form of averaging of the different models. But the problem of this averaging is that it works only if you do it frequently. So like every 1 or 10 iterations, you do the averaging. If you do the average of different models that have done thousands of time steps, it's not going to work. And then finally, we have the baseline of replay, so the X model distillation, but applied on the real data. And instead, for the scenarios, we just take the classic continual learning scenarios, but instead of providing the data, we provide the expert model, so the model trained on the data of that specific experience. And we tested with split MNIST, split CIFAR-10, and CORe50, both in the new classes scenario, where you encounter new classes over time, and in the new instances scenario, where you see all the classes at every time step, but you see new instances. So in the end, we have a large number of settings. We have the joint training, where you have a single experience with all the data, the class incremental, the new instances, and we also did some experiments with multitask, so with the task labels available and multi-head classifiers. This is an example of the synthetic data generation. So here in the first column, you have the original data, then you have the results on joint MNIST, so the data generation, where you have an expert that is trained on the entire MNIST, and then we have for split MNIST, the synthetic data generation, where you have an expert that has been trained only on 2 classes. And just let me zoom in a little bit. So when you have joint MNIST, it's very easy to build, to generate, samples that are resembling the original data. So also when you train using these samples, the performance is going to be quite good. But as you can see here, when you use split MNIST, so an expert that has been trained only on 2 classes, the synthetic data is very, very poor. And this is because of 2 main reasons, let's say. Let's say one main reason is that the model overfits the data since it has never seen the other classes. So think about, for example, classifying a 0 and a 1. You know that a 1 is just a digit that has some pixel in the center, while the 0 never has the pixels in the center. So you can just create these kind of blobs, and they will have a very high score in the probability of being either a 0 or a 1, but they are not a proper digit, right? So when we go and train our model on this kind of poor data, it's not going to work. And actually, this is confirmed also when we look at the accuracy. So here, like for MNIST, we have the joint scenario and the new classes scenario. You can see that in the joint scenario, basically the model inversion techniques are quite close to the expert performance. But instead, in the new classes scenario, it's quite poor. I mean, it's not that bad if you consider that these models have never seen the original data, so it's not that bad, but still very far from the upper bound performance. But also you can see that if you do a simple parameter averaging, like in federated learning, the performance is going to be basically random. And instead, one thing that we notice here, aux data is the technique where you use out of distribution data. You can see that for MNIST, it doesn't work as well because fashion MNIST is not that similar to MNIST. So the model inversion actually works better. But for CIFAR-10, in the new classes scenario, and also in the joint scenario, the out-of-distribution data has actually a higher performance than the model inversion techniques. So like if in general, I think for natural images where we have a lot of large data sets, probably using out-of-distribution data may be good enough, but this is not applicable to scenarios where you don't have a large data set which is similar enough. So now to conclude the presentation, I just want to talk a little bit about the challenges of distributed continual learning and the opportunities. First of all, the challenges, some of them are related to the specific setting of the paper, and some of them are more general. So in general, the X-model distillation is quite complex algorithm because you have this dual model distillation and you are doing this without the original data. So it's difficult to get a high performance. You have the problem of generating training sample, which is very challenging, and especially in terms of diversity. One thing that I noticed is that when you generate a lot of samples with these model inversion techniques, overall, most of them will look quite similar. So you don't have the same amount of diversity that you have in the original data. And so even if you use a very large buffer, it doesn't make that much difference because they are not diverse samples. There is a question of efficiency because this data-free knowledge distillation can be computationally intensive. So it's an important point, but one that we didn't tackle really in the paper. But in theory, instead of doing the knowledge distillation, it could be possible to do some kind of ensembling based on maybe selective pruning or like importance-based estimates of the parameters. So there may be alternatives which maybe have a lower performance, but they are much faster to perform. And then finally, there is the issue of the scenario. So in the paper, we started with a very general scenario where you have access only to the models, but there are several simplifications that are still good for real-world scenarios, but may simplify the problem a lot. Like, for example, you can assume to have mixed experiences. So sometimes you have the expert model, sometimes you have the original data, and this may make it much easier. You may assume to have a shared training protocol for the experts. So you can control the training of the expert to make it easier to combine them afterwards. You may assume to have access to a pre-trained generator. And if you have a generator pre-trained on the real data, you are going to do much better, of course. Or another thing which I think may be useful is to have more frequent communication during training. So instead of sending the model after convergence, you could imagine that the model is sent after each epoch. So this consolidation step, the sharing of the knowledge is done more often, and the different experts will be more similar to each other, so it will be easier to do the distillation. And in general, what we want to achieve is to have this kind of distributed continual learning, which again is a much more general paradigm than federated learning. So the thing that we want to remove from federated learning are things like the frequent synchronization, which requires a large bandwidth, and the single stakeholder training protocol. So the idea that there is a centralized entity that controls the training. Also, sometimes in federated learning, you have things like homogeneity in the model architecture or models that are not able to handle the non-stationarity. So here we're trying to define something that is a bit more flexible, where you have all these agents that are peer-to-peer, so more free, and maybe it's a bit easier to make them converge, but also it's a bit more useful in some setting where you cannot assume to have this kind of centralized control. So the objectives in the end, like as long term, what we would like to be able to do are two. First, the idea of having this marketplace of neural skill, like these expert models that you can take and integrate inside your own continual learning model, so that you can like openly share the model and these skills without necessarily sharing the data or without having to do the training from scratch, which is very expensive. And then the second aspect is that of distributed continual learning. So where you have these multiple agents that are all training in parallel, but they are sharing the knowledge over time, but on their own terms. Okay, so I just want to say that this is one of the research tracks that we are following in the Pervasive AI lab. So if you're interested, feel free to send us an email or contact us with any questions. And this is all that I wanted to say for today. So if you have any questions, I'm happy to answer them. And I'm leaving the link to the paper that you can find on Archive. The scenarios and the pre-trained models are available directly in Avalanche. And these are the easier thing to use because the experts will be downloaded directly from the internet. But you can also look at the original code base where we have all the experiments and the training algorithm. Like if you want to do your own experiments, probably it's better to use the stuff that we are putting in Avalanche. Okay, this is all. Thank you for your attention, and I'm here to answer the questions.
Great. Thank you. That was a great presentation. And as you just said, we are now open for questions. So if you are on Microsoft Teams and you would like to ask a question, please just unmute your mic and ask away. If you are following live on YouTube, just type your question into the chat and I will convey it to Antonio. I will start with a question while people are thinking. I'm curious, when you did the model inversion, what assumptions do you make on the model? One I can think of is many techniques use batch normalization. Do you assume that the model has batch normalization? I guess you assume you can calculate gradients through the model, which I think is a reasonable assumption, but care to comment on that, I guess?
Yes. So yes, we assume to be able to do the backpropagation through the model. So we are assuming to have like a deep learning model. So there shouldn't be any problem here. The batch normalization layers, so we assume to have them because most of the computer vision models have them, but they are not mandatory. Like if you basically, when you compute the penalty for the batch normalization layers, if you list the batch normalization layers and you compute the penalty. So if you don't have batch normalization layers, you are just going to skip that term. But we have other kind of image priors, so
Right.
it's still going to work somewhat. For example, I think I did some experiments in the beginning, like with MNIST and feed-forward models, so without batch normalization, like a simple feed-forward network with 2 layers.
Elaine, looks like you have a question.
Oh yeah. Just wonder what kind of knowledge you use to do the distillation from the X model to the continual learning model.
Okay, so yeah, I didn't put many details here, but basically this here is the are the logits of the 2 different models. So you have the continual learning model at the previous time step, and the expert at the current time step. You first of all, we divide the logits by the sum of the values because you want them to have the same norm. Then you sum them together, And these are the desired logits for the student. And then we do the mean square error, so of y-CORe, the logits from the student, minus the logits from the combined logits of the teachers. Does it make sense?
Yeah. So you just mentioned like it's hard to do distillation because like we cannot access the original data. So what if we like add like you distillation use knowledge distillation include some intermediate layered information? So would that be more helpful for the continual learning model?
Yeah. So if you assume that all the experts have the same architecture, you can do it. There are some paper. For example, I remember, I think it's called PodNet. So it's papers in the they do the knowledge distillation in continual learning, but they do it also for the intermediate layers, and they tend to work better. So one additional challenge that you have here is that you have to combine the two different models. It's not just one. So while combining the logits may be easy, you can just say, okay, you sum them and then you normalize in some way. Combining the intermediate representations may be a harder task, maybe.
Okay. Does that answer your question, Aline?
Yeah, sure.
I'll ask another one. Do you combine the models, or so you combine them sequentially? Have you explored ever combining like more than one at a time, or I guess more than two at a time? I understand the memory constraint of only wanting to do one at a time. I'm just curious if you could it ever make sense to like do two at once instead of one at once? And if your intuition would be that it would be less forgetting if you did it that way.
We didn't try this. So this is something that we discussed in the beginning. Like we were thinking, for example, of taking like a logarithmic memory. I don't know. Instead of taking only the last model, you take the logarithm of I. So the longer the stream, the more models you can keep, but not with a linear complexity, but with a logarithmic complexity, like keeping so the current expert and the continual learning model at different checkpoints. But in the end, we never experimented with this. I mean, I think it should be, I think if you do it in a classic continual learning setting where you have just a single model, it should work better. But here, I mean, you always have, now you have the problem of combining k different models instead of two.
Right.
So yeah, I'm not sure it will improve that much, maybe.
I feel like the distillation process would be more difficult, but potentially the forgetting could be, so there's that trade-off. Interesting to think about. The last question I had is the data always truly the external data? I'm wondering if there's a connection between, how out of distribution is it really? For example, is there some overlap between CIFAR-10 and ImageNet 1K? We have like covariate shifts versus label shifts in the external data, and I know y'all did a very good job at exploring these benchmarks, but I'm wondering if there is a deeper question. If you had a large amount of external data, if you could try to like sample for data that's close to in distribution or not, like you web crawled and you found data that's kind of similar. So I'm wondering if there's more to be gained or explored by looking specifically at the distribution of that auxiliary data and how it relates to the true training data distribution, and whether you could leverage the model's confidence in web crawling to see and get better data. This is not really a question, more just a, do you have any comments on that, I guess?
Yeah. So I think that in general, maybe it's not necessary to have data that is as close as possible to the original one, but it's necessary to have data that is similar to the original, but with a lot of diversity. For example, I've seen even there is a paper, not in continual learning, which is using just a single image with a very high resolution, and then like sampling different views of the image with heavy augmentations. And then it's doing the knowledge distillation using only this source of data, so this single image, and it's still working. I mean, as long as the image contains enough different elements and the transformations, like the augmentation, are good enough. So, I mean, I wouldn't explore too much trying to have something that is close to the original data, but more what are the kind of properties that you need to make the knowledge distillation work, which I think may be different than just having similar data.
Right, and there's two ways of similar. There's similar semantically versus similar like in the pixel space. So that's very interesting. You also brought up a point that makes me think maybe in continual learning we should be focusing on course hit augmentation instead of all these fancy algorithms we had. If one image can do that well.
Yeah. For example, like when we do replay, probably we can keep a very small number of examples as long as we do like some
very heavy,
crazy augmentations. Yeah.
Are there any other questions? Oh, hello.
I just wanted to say hello. Thank you, Antonio, for the talk. Very nice.
They gather together for you.
Yeah.
Awesome. So you said all of this is either on Avalanche or going to be on Avalanche soon?
Yeah. So for the moment, we have the benchmarks on Avalanche and the pre-trained experts, which are downloaded directly so that you don't have to train them. The algorithm is implemented in Avalanche, but it's with an older commit of Avalanche, and I have to clean it a little bit and port it to the main repository. So it will arrive there at some point, hopefully soon.
Awesome. This may be something that we look at in our lab. This is a very interesting question and scenario that you've brought up. So thank you for this talk and everything. If there are no more questions, then I guess I would like to just thank everybody for joining today, and thank you so much, Antonio, for this presentation. I want to put a little disclaimer out, everybody. Please don't forget to explore joining ContinualAI as a full member. For more information on how to become a full member of ContinualAI and what benefits that all entails, please visit the link that's posted in both the YouTube video description as well as the live chat on YouTube. So if you want to join as a full member of ContinualAI, please explore that option more. We have plenty of ways to look at that. And finally, I guess you can catch us again here, same time, same place next week. We'll hear a presentation from Andres Villa on the work vClimb, a novel video class incremental learning benchmark, which sounds very exciting and also very challenging. So can't wait to hear more on that. So thank you again, everybody, and see you next week.
Thank you.